Hello, everyone, and welcome to another AP Chemistry virtual lesson. My name is Michael Faribaugh, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. The focus all this week is on AP exam practice. So if you have been watching lessons this week, you can tell that the general theme is to get as much practice with free response questions as possible. If you have not checked out the 2020 AP testing guide, all you really have to do to find this document is to do an internet search for that particular phrase, and you should discover the 2020 AP testing guide, which includes lots of great information for you to prepare for exam day. So you can go to cb.org/AP2020. and you can find quite a variety of resources. So you'll notice in this resource that you'll need an AP e-ticket, an AP exam e-ticket to test, and you should receive it by email, but you can always access the information at myap.collegeboard.org, and you can double check that you are set up to receive emails from the College Board. When you do take the online AP exam this year, you have three options of submitting your responses to the free response question. You can either be typing in a document and then cut and paste into the response window and then submit, or you can save the document that you are working on with all of your typed responses and then attach that and click submit. Or if you prefer to handwrite your answer, then you can take a photo of your handwritten work and then attach the photo and then click submit. You can go to cb.org/AP demo, and then you can try lots of different forms and see what feels comfortable to you so you can prepare for what you're going to do on the day of the exam. So again, that's an important practice. For chemistry specifically, you would need besides your e-ticket, you would need a periodic table, and you can go to cb.org/AP exam day docs, and you can find the periodic table along with the AP chemistry equations and physical constant sheet. And there's also a keyboarding tip sheet. So for example, if you're typing on a computer and you're trying to figure out what's the best way to represent formulas or equations or show your work, the keyboarding tip sheet will give you some ideas about that. You can also go to cb.org/AP open book tips for information about how to organize yourself and what you can do to help you best prepare for an open book, open note exam. Again, you should receive information for each of the AP exams that you are taking from the College Board with your e-ticket 2 days before the exam. So again, feel free to make sure that you all are registered and set up. You can go to, log into My AP. And if you need the checklist, you can go to cb.org/AP checklist and download that. And that gives you lots of information to kind of summarize preparation. Remember that AP Chemistry will be on May 14th. And there are 2 free response questions. The first free response question is 25 minutes, and they give you 5 minutes to submit. And the second free response question is 15 minutes, and again, 5 minutes to submit. So you'll submit your answer to the first question and then answer the second question. So once you submit your answer to the first question, then you can't go back to it. Next week, all next week, we're going to be doing AP Prep Week. And what I'll do in our lessons next week is give you some sample free response questions and then actually give you the time in real time to take the question, answer the question. So we're trying to simulate that experience, that test taking experience in our lessons next week. All right, this just talks about, giving yourself a good environment for testing and minimizing distractions and making sure you have good access to your internet or cellular connection. Talks about the check-in process where you log into the exam with your e-ticket, and then you would answer the question. And again, we'll be talking about the format and the practice next week. talking about managing your time, submitting your response. So if you're looking for more practice problems, you can log in at myap.collegeboard.org. You can click on AP Classroom, and then you can click here for optional student practice. So practice answering free response exam questions, and then after you type in your response to a particular FRQ and you click submit, then you can say yes, review, and you can see scoring guidelines. So AP Classroom has some practice problems that you can do for various AP subjects. All right, well, let's go ahead and get started with our lesson for today. Now, in the previous lessons that I have taught this week on Monday and Thursday, I have given you 3 long FRQs. What I'm going to try to do today is to give you 6 shorter FRQs. So let's go ahead and get started. Remember that this is a time to pause the video after I have presented the question, because I'm going to go over the answers more quickly than you have had a chance to process. So please pause the video and answer this question. And we're going to try to get 6 questions, short questions done today. Okay, so this is the first question. You can see a picture of a beaker of sand with a thermometer in it and a butane burner underneath that is heating the sand. And there's information about what is happening. And there are parts to this question. This is part A and B. And there is also a part C and D. So again, at this point, you are going to answer parts A, B, C, and D on your own. And then go ahead and click play when you are ready to check your answers. Okay, I'm going to make the assumption that you have already answered parts A, B, and C, and D. Here we go. A student is asked to determine what mass of butane, C4H10, needs to burn in order to raise the temperature of a 1,650 gram beaker of sand by 180 degrees Celsius. The student is provided with the equipment shown below. Part A, calculate the amount of heat energy needed to raise the temperature of the beaker of sand by 180 degrees Celsius. Assume that all the heat energy from the burner is transferred to the beaker of sand and that the specific heat capacity of the beaker and sand together is 0.810 joules per gram degree Celsius. We're going to use the equation for calorimetry, which I think you are familiar with, but if not, I'll go ahead and give it to you. Q, which is our heat, equals mc delta T, where m is the mass of the object that is being heated, C is the specific heat capacity of that object, and delta T is the change in temperature. So we are given a 1,650 gram beaker of sand. We are also given that the specific heat capacity of this beaker and sand is 0.810 joules per gram degree Celsius. And they want us to raise the temperature by 180 degrees Celsius. So now all we have to do is multiply these 3 values together. The grams will cancel out, the degrees Celsius will cancel out, and we get our answer in joules. If you have done this on your calculator, then you should have gotten 240,570. I'm going to round this off based on the measurements that I'm given to 3 significant figures. So you could either report this as 241,000 joules, or you could say 241 kilojoules. Either one of those would be acceptable. All right, moving on to part B of this question. The student runs the experiment and collects the data shown in the table below. Calculate the number of moles of butane. So we're going to focus on this part of the data table. How many moles of butane were used in this experiment? So I'm going to subtract these 2 numbers, which is the difference between how much the butane burner weighed before and after the combustion. And when you subtract numbers, you have to keep the same decimal places, or you would use the fewest number of decimal places if they were different. So I'm going to have 7.06 for my answer for grams of butane, but I'm not done yet. I've got to go to moles. And that has 3 significant figures, so 7.06 grams of butane, and they do give us, in this problem, the formula of butane, although it was not listed in the table itself, it was up there in the stem of the question. So carbon weighs 12.01, hydrogen weighs 1.008, so you multiply carbon times 4, hydrogen by 10, and you get 58.12 grams of butane per mole. 3 significant figures in our answer. So 0.121 is the answer to part B. That's moles of butane that were used in the experiment. Now, moving on to part C, we are given a balanced equation for the combustion of butane. So this right here, the delta H for the reaction, what that tells us is that 2,659 kilojoules of heat is released for every 1 mole of reaction, or in this case, for every 1 mole of butane. Now, we already have 0.121 from the answer to part B. That's how many moles of butane were used. We're going to calculate the amount of heat energy produced by the combustion of butane based on the information in this balanced equation. So you could put 2,659 kilojoules on the top and then 1 mole of butane on the bottom. I'm just doing this through the mole of reaction, but it doesn't change the math. So 0.121 times 2,659 gives us 322 kilojoules. Now let's compare our answer to part A, which was 241 kilojoules. That's how much heat was needed to raise the temperature of the beaker of sand. And then, based on our recent calculation, 322 kilojoules of heat was actually released during the combustion. So let's see if the claim in part D of this question can be something you agree with. The student claims that some of the heat energy produced by the combustion of butane was lost to the air surrounding the system. Do your answers to parts A and C support this claim? Well, it looks like the output of heat from the combustion of butane was actually greater than the amount of heat needed to raise the temperature of the beaker of sand. So I would say yes, the answers to part A and C do support this claim or this hypothesis. The amount of heat generated from the combustion of butane is greater than the amount of heat required to cause the temperature to change in the beaker of sand. So this indicates that some of the heat from the combustion of butane did not go into the beaker of sand, but was lost. Okay, so we are now done with our first short question and on to our next short FRQ. And this is only on one screen. This is it, just parts A and B. So take a moment, read this question, pause the video, and then when you are ready, press play. Do not just watch me solve it. Go ahead and take the time to solve this yourself. All right, I'm going to assume that you are ready to check your answers to this question, and we're going to start with part A. Answer the following questions about the solubility of AgCl, which is silver chloride. The value of KSP for solid silver chloride is 1.8 times 10 to the negative 10. Part A, calculate the value of the concentration of silver ion in a saturated solution of silver chloride in distilled water. I'm going to go ahead and write the equation for the dissolution of silver chloride in water. So it splits up or dissociates into positive and negative ions, and we have our KSP. Now, this is not anything more than just a 1-to-1 mole ratio here between the molarity of the silver and the molarity of the chloride. So we're not doing x times 2x squared like we've seen in other examples where there's a 1-to-2 ratio. This is just x squared. So if we're solving for the concentration of silver or the concentration of chlorides, could be the exact same number, we're just going to take the square root of the KSP value. And that works out to be 1.3 times 10 to the minus 5 moles per liter. Okay, so that is the answer to part A. Let's move on to part B. The concentration of chloride in seawater is 0.54 moles per liter. Now notice that this number here is much higher than 1.3 times 10 to the negative 5. So that would be the concentration of chloride if you were just dissolving silver chloride in distilled water, pure water. The fact that there is already a rather high concentration of chloride present in seawater. I'm going to go ahead and just finish writing this equation for the dissolution. This relates to both Le Chatelier's principle and what is known as the common ion effect. So if we have a much higher concentration of chloride present in seawater, and now we try to dissolve some silver chloride in this seawater, Le Chatelier's principle says that when you have an extra amount of product added, then the equilibrium position will shift in the direction of the left toward the reactants. So that means that, as we can already tell, that's coming up in part II of this question, silver chloride is going to be less soluble in seawater because there is already this extra concentration of chloride present. So we're going to do the math in part I, and then we're going to explain why in part II. Okay, let's go ahead and do the math. So we still have our KSP, but now we are not doing X and X. We're going to go ahead and take the 0.54 that we are given in this problem, and that is going to be our concentration of chloride that is already present. So when we plug in 0.54 and we solve for silver, we're going to get a much lower concentration of silver than we did in part A. And sure enough, if we do this math, we get 3.3 times 10 to the minus 10. So that lower concentration tells us that the silver chloride is much less soluble in a solution that already contains a fair amount of chloride ions. This would come from Unit 7 in the AP Chemistry curriculum, the common ion effect. So it says here that the solubility of a salt is reduced when it is dissolved in a solution that already contains one of the ions present in the salt. The impact of this common ion effect on solubility can be understood qualitatively using Le Chatelier's principle or calculated from the KSP for the dissolution process. So we've done both. So the seawater has a relatively large concentration of chloride ions in it. The solubility equilibrium is shifted toward the left, making the solid less soluble in a solution that contains a common ion in it. So that was the answer to part II of part B. Okay, I am now going to give you the next short free response question. And this will be on 2 screens. So here is the question. It starts, and there are parts A, B, and C. And then there is also a part D on the next slide. So here is part D. Okay, so if you are ready to check your answer, then keep watching. But if you have not solved this problem yet, pause the video, solve the problem, and then press play when you are ready to check your answers. Okay, I'm going to assume that you are ready to check your answer. So here we go. A new element with atomic number 116 was discovered in the year 2000. In 2012, it was named Livermorium with the chemical symbol LV. Although livermorium is radioactive and short-lived, its chemical properties and reactivity should follow periodic trends. Part A. Write the electron configuration for the valence electrons of livermorium in the ground state. Now here we have a periodic table, and we should know that we have essentially what I would call the S block over here. which would be like these first two columns. We have the d electrons in this region right here. And then except for helium, which is going to end with 1s2, we have the p orbitals. And then you can't see it on this particular screen. I have not included it, but the lanthanides and the actinides, that would be the F block down there. So in terms of the rows of the periodic table, except for the D and the F block, whatever row you are in is the energy level. So for example, second period, we have 2s and 2p. Third period, we have 3s and 3p, and so forth and so on. Now, Livermorium is way down here. Okay, that's where Livermorium is located. So the previous noble gas, which again is kind of covered up here on this slide, is radon. So radon, that contains 86 electrons. Well, what comes after radon would be francium and radium. So I'm going to go ahead and call this 7s2. If I were to keep going around this part of the periodic table, I would also have to squeeze in what you can't see, which is the 5f14. 6d would be all of it, so 6d10, and then I have to go 7p, but I have to stop right here. So 1, 2, 3, right there, be 7p4. Okay, if I wrote this as my answer to this question, then I would not get credit because I wasn't paying attention. Let's read that question one more time. Write the electron configuration for the valence electrons of Livermorium. So not the entire electron configuration, just the valence electrons. Now, this is the correct electron configuration for the entire element, Livermorium, but we're just focusing on the electrons in the outer shell, which in this case are going to be the electrons that have the highest energy level 7. So we're focusing on the 7s2 and the 7p4. So that's 6 valence electrons, and that is the correct answer to part A. Part B, according to periodic properties, what would be the most likely formula for the product obtained when Livermorium reacts with hydrogen? Let's go ahead and focus on the periodic properties, and that would be not a period, not a horizontal row, but rather a vertical column or a group. So Livermorium is at the bottom of group 16 on the periodic table, which starts with oxygen. Now, as you, I'm sure, know this already from the formula of water, oxygen has, like the other members of this group, 6 valence electrons. 1, 2, 3, 4, 5, 6. And if I have, let's say, a hydrogen atom with 1 valence electron and another hydrogen atom with its valence electron, then I can form the Lewis electron dot structure for water. But I could similarly, I could change and go down the group and say, well, the formula of the hydrogen and sulfur compound is H2S. There's also H2SE for selenium, H2TE for tellurium, H2PO for polonium. And so the correct answer to this question, the formula for the product obtained when Livermorium reacts with hydrogen is based on the periodic properties of this 2-to-1 ratio between hydrogen and the member of group 16. All right, part C is also related to periodicity and periodic trends. So we are given that the first ionization energy of polonium is 812 kilojoules per mole, and we have to compare that number with the first ionization energy of Livermorium. So if it's greater than, less than, or equal to, we have to justify our answer in terms of Coulomb's law. So you cannot say something like ionization energy decreases as you go from top to bottom down a group. That is a trend, but that's not using Coulomb's law. So Coulomb's law will help us because Coulomb's law relates the attraction between charged particles to either charge or distance. Now, if I go from Livermorium to polonium, I now have a lower energy level for the shell. So we go from level 6 to level 7. You can imagine that if I have a nucleus and I have a particular atom, this is the electron in the valence shell that is going to be removed. That's what ionization energy is all about. So what do you think happens when you go from, let's say, level 6, polonium, to level 7, Livermorium? Hopefully, you know that as you increase the energy level, that the valence electrons are now going to be located farther away from the nucleus. So we're focusing on the distance. We're not talking about charge. We're not talking about protons. We're talking about level 6 versus level 7. And these electrons that are farther away from the nucleus are easier to remove. So therefore, my prediction would be that Livermorium would have an ionization energy that is less than that of polonium, but I have to talk about atomic structure. I cannot just say ionization energy decreases as you go down the group. All right, so here's what I said. Less than, again, I answered the question that was being asked. Do not forget that part. When you're answering an AP exam question and they ask you to make a prediction, don't just jump straight into your explanation that you actually forget to answer the question that was being asked, because then that's not a complete answer to this question. So make your prediction and then justify. So I said the valence electrons in Livermorium are located at a higher energy level, which is level 7, as compared to polonium, level 6. The valence electrons in Livermorium are located on average at a greater distance from the nucleus, again focusing on Coulomb's law and the distance. Therefore, the attractive force between the valence electrons and the nucleus decreases by the inverse square of the distance between them. All right, there was a part D to this question. Let's take a look at it. This is a mass spectrum, and there are 3 isotopes of Livermorium that are featured in this question. So at the top of little bars here in the bar graph, these are the mass numbers. Now on the vertical part of the axis, we have number of atoms. So it's a sample of 10 atoms. Well, that means that if I'm going up to 2, that would be 20% of the total. If I'm going up to 3, that would be 30%. And then going up to 5, that's 50%. So we're going to just do a weighted average. Okay, we're going to do a weighted average. We multiply each of these numbers for the mass numbers by the percent as a decimal. So I did 291.2 times 20%, which is 0.2. And then I continued 292.2 times 0.3, that's 30%. I'm adding these portions together for my weighted average, 293.2 times 0.5. And my grand total is the weighted average, which works out to be 292.5. All right, so we have now answered this particular short FRQ. Next question coming up. All right, so here is your brand new question, and there are parts A, B, and C to this question. So here is part A and B. And here is part C. So pause the video, read the question, answer the question, and then press play when you are ready to check your answers. All right, I'm going to make the assumption that you have already done that. Let's take a look at part A of this question. A student has 100 milliliters of 0.400 moles per liter copper sulfate, CuSO4 aqueous, and is asked to make 100 milliliters of 0.150 molar copper sulfate for a spectrophotometry experiment. So I'm going to go ahead and call this solution concentrated, and I'm going to call this solution dilute. So at some point, we have to figure out how much of this concentrated solution do we need to prepare 100 milliliters of the more dilute solution at the lower molarity. Now it says that the following laboratory equipment is available, and they list a centigram balance, just an electronic balance, weighing paper, which is just simply to transfer the solid to something you can actually put it on and then eventually transfer it from the weighing paper to the container. We have a funnel, and then we have various beakers. We have a graduated cylinder, volumetric flask, burette, and distilled water. I don't need to worry about the equipment for part A. I just have to do the math. You should know that when you are given volume and molarity, volume times molarity equals moles. Assuming that your volume is in liters, volume times molarity equals moles. Okay, so we're going to calculate the volume of this concentrated solution that is required to prepare the dilute solution. Now, we know that we need to make 100 milliliters of this dilute solution. We know that the concentration is 0.150 moles per liter. And I've written on the bottom, instead of 1 liter, I've written 1,000 milliliters, just so I can get my units to cancel out. So I need 100 times 0.15 divided by 1,000. I need 0.0150 moles of copper sulfate. I am not weighing out a solid. I don't think I need the weighing paper at all. They just gave us more information about the equipment that was available. I need to get that particular moles of copper sulfate from a more concentrated solution, which happens to be 0.4 moles per liter. So moles on the bottom. And again, I'm using 1,000 milliliters instead of saying 1 liter on top, because I want my answer to come out in milliliters. Now you could write 0.0375 liters, that's fine. They did not specify the units, they said calculate volume. So I did this math and I got 37.5 milliliters of the solution. If you are a good chemistry student that has solved a variety of molarity problems before, you might be asking the following question. Could we have done this calculation using an equation like this? And sometimes it's written in chemistry textbooks or in classrooms as M1V1 equals M2V2. I'm just writing C for concentrated solution, and then writing D for dilute solution. So we know the molarity of the concentrated solution. And again, M times V gives me moles. So when I do a dilution, I'm not changing the number of moles of the solute. This particular volume, right now, we don't know what that is. That's what we're trying to find. The molarity of the dilute solution is right here. And the volume of this dilute solution that we need is right there. So I can go ahead and plug in my numbers. I'm still going to get, if I do this math correctly, the same answer I got before, which is 37.5 milliliters. Okay, so now I've got to take a look at the equipment. In part B, I know I need 37.5 milliliters. Briefly describe the essential steps to most accurately prepare the solution. Well, let me go ahead and see if I can do my best. So forgive my lack of artistic talent here. I'm going to skip the part about the balance on the weighing paper because we are measuring volume here. So you have a funnel. Okay. We have a beaker. We have actually two different kinds of beakers. We have a graduated cylinder. And we also have a volumetric flask. And we have a burette. This is probably clamped in there somehow. something like that. There's our burette. And then we have some distilled water. Okay. Most accurately, now 37.5 milliliters, I would probably use either a graduated cylinder or a burette, but typically the burette has finer divisions on it. So typically a burette will go out to the 100th place, whereas depending on your graduated cylinder, probably goes out to the whole number of milliliters or maybe the 10th place. So I'm going to go with our burette. We're going to take our 37.5 milliliters. Let's measure it with the burette. Let's transfer it to the volumetric flask, and then we can add distilled water until the final volume is equal to 100 milliliters. So let me go ahead and erase my lovely drawings. Use the burette to dispense 37.5 milliliters of copper sulfate solution into the volumetric flask. Fill to the mark with distilled water. This particular question happened to be worth 2 points. And as you can see on the scoring guidelines, you got 1 point for choosing the burette, and you got 1 point for choosing the volumetric flask and talking about how you would fill it to the mark. All right, there was a part C of this question, and here it is. The student plans to conduct a spectrophotometric analysis to determine the concentration of copper in a solution. Now, the solution has a small amount of cobalt nitrate as a contaminant. So we don't want the absorbance of the cobalt. We want the absorbance of the copper. The student is given the diagram below, which shows the absorbance curves for the aqueous solutions of cobalt and copper. So this is what we want. Now, the maximum absorbance for copper would be a good thing, like right about here. But I cannot set my spectrophotometer to 800 nanometers as a wavelength because it only goes in the range of 400 to 700. So I've got to work with this window right here. What wavelength should the student use to minimize the interference from the copper? So I don't want to pick something like this because that would be absorbing cobalt. I want the copper, not the cobalt. I may have just said that backwards earlier, sorry. I want the copper, not the cobalt. So I actually want somewhere in this region would be good. That way it can maximize the copper and minimize the contaminant, the cobalt. So acceptable answers for this question would be anywhere between 650 and 700 nanometers. Again, trying to emphasize that we're trying to get the absorbance of the copper. So you want the cobalt to be really low and the copper to be relatively high and still fall in this range. Okay, we are moving on to our next short free response question. This has parts A, B, and C. Here is parts A and B. So take a look at that. And here is part C, which involves a particle diagram. Okay, so I am going to make the same assumption that you have already paused the video, that you have already solved parts A, B, and C on your own, and now you are ready to check your answers. So here we go. The boiling points, dipole moments, and polarizabilities of 3 hydrogen halides are given in the table above. Part A, based on the data in the table, what type of intermolecular force among the molecules HCl, HBr, and HI is able to account for the trend in boiling points? Justify your answer. Now, I'm going to show you an example of a student who understands good chemistry but doesn't read carefully. So we know that HCl, HBr, and HI are polar molecules. If they were non-polar molecules, they would have a dipole moment of 0. So we know that they're all are polar molecules. It's kind of obvious that there are 2 atoms in the molecule and the 2 atoms are different. So we have a difference in electronegativity. These are polar molecules. So a student might ignore what it says in the question and go like this. They all experience London dispersion forces and dipole-dipole forces. Now, that is not an incorrect statement. That's fine. But if you write that, are you answering the specific question that is being asked here? They need you to talk about the trend in boiling points. So let's go ahead and take a look at what we have here. We have polarizability, which I'll talk about in just a second. We have the dipole moment, which indicates how polar the bond is, and then we have boiling points. I think you know this from Unit 3, which is on intermolecular forces, that the higher the boiling point, and that's what we're seeing right here, typically that means the stronger the intermolecular forces. So HI has the highest boiling point in this set. Could I then go ahead and say that the reason why HI has the highest boiling point is because it is the most polar molecule? No, the data does not suggest that it's the most polar molecule at all. It has the smallest dipole moment. So I cannot make an argument about dipole-dipole forces being stronger in HI because that's not what the data says. Now, what exactly is polarizability? Well, polarizability has to do with the size of the electron cloud. So effectively, what polarizability is how likely is the electron cloud able to be distorted? The one textbook that I use in my classroom talks about like the squashiness of the electron cloud, or the ability of the electron cloud to be distorted. So if I were to go ahead and draw hydrogen, which is a relatively small atom, and let's say it's bonded to chlorine. I'm going to go ahead and draw chlorine as a little bit bigger. It has a certain polarizability. Now, I have other polarizabilities here. Okay, this is HCl, HBr, and HI. So if HBr is more polarizable, and we know this from periodic trends, bromine has a larger electron cloud. And if iodine is even more polarizable, it also has a larger electron cloud. That's what you have to talk about if you're going to justify or account for the trend in boiling points. So they're giving you data. You just got to pay attention and use the data and your understanding of these concepts. So here's what I said. London dispersion forces account for the trend in boiling points. As the size of the electron cloud increases, the polarizability of the molecules increases, and so does the boiling point. London dispersion forces depend on the polarizability of the molecules. More polarizable molecules have stronger intermolecular forces. So that's that. Okay, there was a part B to this question as well as a part C. Let's move on to part B. Based on the data in the table, a student predicts that HF would have a boiling point of around 174 because they're thinking, okay, they're getting smaller, 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 smaller. But in fact, the boiling point of HF turns out to be 293. Explain the failure of the student's prediction in terms of the types and strengths of the intermolecular forces that exist among HF molecules. I will take you back to Unit 3. If you watched that video talking about intermolecular forces, and this is a very common graph you see when discussing hydrogen bonding. So the fact that oxygen, fluorine, and nitrogen form these hydride compounds that tend to have rather unusually high, based on the trend in boiling points of the other hydrogen compounds that are in the group, there must be some reason for that. So hydrogen bonding is a strong interaction that occurs between molecules. And the kind of molecules we're talking about are when an H atom is directly bonded to either a nitrogen, oxygen, or fluorine. And then that connects with another molecule. So the nitrogen of one molecule connects with the hydrogen on another molecule. So let's go ahead and use hydrogen bonding in our answer. to part B. HF molecules experience London dispersion forces and hydrogen bonding. The hydrogen bonding between HF molecules is stronger than the dipole-dipole forces and the London dispersion forces in the other 3 molecules, and this, the hydrogen bonding and the strength of that attractive force, this accounts for the fact that HF has a higher boiling point. All right, there was a part C of this question. We have to show what happens after vaporization has occurred. So we're going from a liquid to a gas. So vaporization. All right, I'm doing this wrong. I'm just trying to talk about a common misconception that students might have. Some students really are confused about what bonds you break when you undergo certain types of phase changes. So we are not doing this at all, okay? We are not breaking the molecule up. Any student that were to draw a white circle separated from a black circle would not get credit for this, but you should show that they are distributed randomly throughout the box, because that's what gas particles do. They just kind of move around rapidly and randomly in all directions, but they should still be undissociated. They should still be intact diatomic molecules of, in this case, Br. So we had to draw 5 HBr molecules in the box on the right and just randomly, separated around. Okay, we have time for one last FRQ, and it has just this, just parts A and B. That's it. So take a look at this question, pause the video, answer this question, and then press play when you are ready to check your answers. All right, I am making the assumption that you have done that and you are ready to check your answers, so here we go. The structural formulas for glycerol and trichloropropane are given above. Both compounds are liquids at 25 degrees Celsius. For each compound, identify all types of intermolecular forces present in the liquid and explain why glycerol has the higher boiling point in terms of the relative strengths of the intermolecular forces. Now, we had just talked about HF in the last question involving hydrogen bonding. Remember, it's hydrogen directly attached to either A, fluorine, nitrogen, or oxygen. So we're going to talk about hydrogen bonding again. These molecules are both polar, but we have hydrogen bonding in between molecules of glycerol, and we do not have hydrogen bonding in between molecules of trichloropropane. So here I go. This is the official scoring guidelines answer to this question. Each substance has intermolecular London dispersion forces and dipole-dipole forces. Glycerol also has hydrogen bonding, and so the presence of the hydrogen bonding in glycerol results in the total intermolecular forces in glycerol being stronger than the total intermolecular forces in trichloropropane. If all you did was say hydrogen bonding, you would not receive full credit because you have to identify the IMFs in each liquid. So always mention the intermolecular forces for each substance before you go on to make your comparison and justification or explanation. All right, and then the part B, which is going to remind us of something we saw earlier in this lesson. The very first question I showed you today had to do with a beaker of sand that was being heated with a butane burner. So we're going to involve Q equals MC delta T again. It says the enthalpy of combustion for glycerol is negative 1654 kilojoules per mole. What mass of glycerol would be needed to be combusted to heat 500 grams of water, so there's my mass, from 20 to 100 degrees Celsius? That would be a delta T of 80.0, and they've given us the specific heat capacity of water. If I multiply 500 times 4. Oh, I think I wrote that wrong, 814. Sorry, I'm not sure if that's a typo on my part. Yeah, I think it should be 184, excuse me. Anyway, that is the correct math. It is 167, so I apologize for that. I think it's supposed to be 4.184, so ignore that part. Sorry about that. But this is the correct math. It's 167,360 joules, which I rounded off to 3 significant figures. I could say 167,000 joules or 167 kilojoules. Okay, that is the correct answer to part A. Sorry about that typo on the screen. So if 167 kilojoules is how much heat is needed, we have to get this from the combustion of glycerol. So for every 1 mole of glycerol, 1,654 kilojoules of heat is generated. Let's put kilojoules on the bottom and moles on top. This is our chemical formula of glycerol. So we have C3, and then 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and we have 3 oxygens. So go ahead and do that molar mass calculation. And now we're going to cancel off the units of kilojoules and moles, and we should get our answer. So it takes 9.30 grams of glycerol to be burned to raise the temperature of 500 grams of water from 20 degrees to 100 degrees. All right, that does bring us to the end. Thank you for hanging in there with me. Hope that was good FRQ practice. Again, a link to helpful chemistry resources. Now, I will tell you, so again, this has been Michael Faribaugh from Albemarle High School in Charlottesville, Virginia, that on Monday and all next week, we're going to be doing timed practice for FRQs. So if you join us next week, you will see me giving you time to actually solve the problem, and we'll try to simulate as much as possible the AP exam test taking experience. So enjoy your weekend. I'll look forward to seeing you back here on Monday. Thanks for watching.